of, when you're using a film screen combination, 99% of what creates the image is light, not X-rays, right? Less than 1% or 1% is actually what is creating the image. Most of it is X-rays. All right, and so the first thing that will come to mind when you look at it, when you think of intensifying screen, should be patient dose reduction. Okay? Is that because that's what intensifying screens do. If you don't, then you have to use a lot of X-rays, lots of radiation to be able to create an image. Alright? Just amplified the beams, reduce patient dose, X-rays convert to light. 99% of the images come from light, visible light. 1% from direct X-ray exposure. Alright? They were first developed by Thomas Edison in 1896, so only a year after, only about a year after the discovery of X-rays is when they were discovered, or when they were first developed by Edison. So that was only a year after, so things are happening very quickly. Alright? Now, the type of intensifying screens that Edison developed, they were only used for large body parts, the abdomen, the chest, and later on,
Bless you.
Bless you.
so if you have that question of why they stopped using it, it's not that they stopped using it, it's just the compounds that they were using back then, they were not useful for small body parts. Okay, hands, feet, that type of stuff. They were only used for larger body parts. We okay with that?
Mm-hmm.
Yes, Garrett?
I just want to ask, why didn't they use it for?
That's what I said. I'll explain it later on. Okay? Alright. Okay. So, when we look at the construction of the screen, okay, very similar, if you look at it, don't get confused, very similar to the way the film is constructed. Okay? So, you have a base, okay, just like film does. Now you have here something that this is not found in the film, a reflective layer, and then you have a phosphor layer that you can think of, well, the phosphor layer, it will be like the crystal halides type of layer. Okay, that's the active part of it is in the phosphor layer. You also have, just like film, it will have a protective coat to protect the phosphor from being lifted off when handling the intensifying screens. All right, let's see. Sizes are important for you to memorize, just have an idea, okay? Okay, nanometers. This is not millimeters, by the way, nanometers, 150. All right.
Oh, nanometers.
Okay. All right, the base. The base, just like film, the base, just like the film is going to be made out of polyester plastic. It's just plastic, okay? Very strong plastic. And just like film, if you try to rip that plastic, you will crack your hands. You will not break it. It will probably be easier to rip that piece of plastic. It will be easier to rip that Bouchon, that Merrill's book that you have right in front of you. Okay, it's very strong plastic. You're not gonna rip it. Okay, you might deform it, but rip it. No. All right, proximal thickness 1 millimeter. Okay,
What's millimeter?
1 millimeter, not 1,000. Right? So that's what I made the correction with previous stuff. 1 millimeter. Okay. Specifications. Okay, this is specifics about the base. Take some time today. Tough. Okay. Okay. It has to be chemically inert. What is the meaning of chemically inert? That is not going to react with anything. It's not going to react with the phosphor. It's not going to react with the film when they're in contact. It's not going to react with the X-rays. It's not going to react with, it's just inert. Inert means that it just doesn't do anything. Okay? It's just like, when you're tired after a test, you're just inert. That's kind of how it is. Inert, right? when you're really tired, when you know you've done your workout or whatnot, or you've been with your child all night, and the child has been crying, and you're really inert in the morning. Okay, well that's what this is.
Inert.
Right?
Oh, okay.
Inert. Okay. All right, tough. All right, that's what I was explaining before. That it's strong. You're not gonna be able to do that. Flexible, on the other hand, so it's malleable. Okay, just like paper. Okay, and you got with plastic. Now it takes to form back again. So same thing there. Very flexible in that respect. He has to be radiolucent. You have to allow the X-rays to go through. Let me go back here. You can see that. You have to allow X-rays to go through so the X-rays can interact with the phosphor. Right? Yes? X-rays are coming from this end. Interact. They go with the base. Nothing happens because it's inert. Right? You go right through it. And nothing happens because it is also radiolucent. Nothing is stopping the X-ray. So the X-ray will go through, interact with the phosphor, and then the phosphor will absorb that X-ray energy and emit light in response to it. So that's what we have here. So it's flexible, it's radiolucent. Okay, so those are some of the characteristics you have with the base. Any questions about the base? No?
No.
Okay. All right. So now the reflective layer. All right, so we're moving down. So you have the base. Now we're going to go to our reflective layer. This is the layer that is attached to the base. Right? All right. So remember that when X-rays, we used this term before, isotropic. You have heard before when we talked about the electrons and the X-rays being created in the target. They are created isotropically, meaning that they are going everywhere. The same type of issue, okay, happens when X-rays interact with the phosphor. When they interact with the phosphor, the light, the visible light that is emitted, it will be emitted isotropically. It will go everywhere. So let me go back to this slide here. So X-rays come here, boom, 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 boom. And when they interact with the phosphor, light will be created isotropically. So it will go this way, this way, this way, this way, this way. It's going everywhere. And so the layer that we're studying here, the reflective layer, what is there for is to reflect back that light back into the film. The film is going to be here, next to the screen. See it? And so you have this, think of it as a mirror. Not really a mirror, that's the same kind of analogy here. You have a mirror here, and when the light goes here, boom, it bounces back. So light is not wasted. Make sense?
Mm-hmm.
Okay. Yes?
So once light goes through the base, it can't go back out
What
because
is
of
it?
the reflective
What
layer.
is it? I'm sorry?
Oh, so when the beam goes through the base,
Uh-huh.
then it can't go back up through the base because of the reflective layer.
Remember, this is not light what is going here. This is X-rays.
I mean, the X-rays,
when
excuse
the
me.
X-rays are going here, the phosphor will absorb, will suck the energy of the X-ray. Right? Okay? Suck the energy, and then what the phosphor will do in response to that, it will emit this shining, invisible light that you saw there, the green light. And so that light, you don't want it to go to waste. And so what happens is you have this reflective layer to point it back down. Make sense?
Yes,
Everybody?
thank you.
So here's where we are with the reflective layer. The reflective layer is a very thin layer of magnesium oxide. Titanium dioxide has also been used, but titanium is very expensive. Any of you ladies have titanium jewelry? Yeah, she says. Fantastic, very expensive. More expensive than gold. Sometimes, I don't know what the price of gold is. The titanium is very expensive. Yeah, very expensive. So anyway, so they don't typically use titanium. They use magnesium. Magnesium is a lot cheaper. Magnesium is the stuff that you take when you stomach upset. Okay. Acid reflux, same magnesium. Yeah, different chemistry. All right, so it's cheaper, right? And so what it does, it reflects the light back to the film, just like I pointed at you. Okay. And this allows for the reduction of patient dose, right? Because the light is not wasted, it's not going anywhere. And so you're maximizing the amount of light that is pointed at the film. Okay. The problem is this. There is loss of image sharpness. So resolution with any screen, write this down, write yourself this note. With any screen, when you're using any type of a screen, you will lose resolution. Okay, there is a loss of resolution, and that's what I was saying the other day. When you compare direct exposed films to screen images, direct exposed film looks always sharp. I mean, they're immaculately nice pictures, but the price is patient dose. Now, on top of that, on top of having the screen losing resolution, you add this reflective layer, is going to even more, the image is going to lose sharpness. Okay? If you think about it, if we go back here to this picture here, see, X-rays are coming down, right? Interacts with a phosphor. The phosphor creates light, and the light goes this way. Everything, right? But it also goes back up. And so you have this reflective layer to point the light back down. But the light photons are not hitting the same spot on the film. Mm-hmm. Some of the light photons are hitting here, some are hitting here, some are hitting here. Make sense? Mm-hmm. And that, that sharpness, that if all the photons were hitting in the same spot, and we're talking microscopically here, but still, now you're talking about millions of phosphors doing the same thing, and so resolution is lost because of that. Are you with me?
Yeah.
All with me? Okay, good. All right, so you will have loss of resolution when you add this reflective layer. We're going to see later on that the later developed intensifying screens didn't have a reflective layer. Okay, I'll point it at you when we get to that point. But the first screens that were developed, they all had this reflective layer. The reflective layer is approximately, take a look, 25 micrometers, so very thin. 25 micrometers, and it's thinner than your hair. It's really thin. It's just a faint slight layer. All right, so this is what I was explaining before, but take a look at the picture now. You have the base. Okay, let's follow it here. There's nothing to write here, just pay attention. Here's the X-ray coming down. Okay, interacting with the phosphor. The phosphor will absorb that energy. Okay, after it absorbs the energy, it will emit light. Okay, the light is emitted isotropically, so it's going everywhere. So some of the light hits. Here's the film. Okay, so it's hitting the film, hitting the film, hitting the film, but some of the light is going back up, and so you have this reflective layer to send it back down. But now, take a look. See, this is a wider space where what one X-ray photon had done, now you have it in all this wide area here. Okay? Okay, the protective coat. The protective coat is applied over the phosphor layer to protect the phosphors. Okay? And protect it from what? From physical trauma that they receive from technologies. When you open the screens, you put your fingers in there, and so if you were just doing that, grabbing the film, and you pull and scoop off the phosphorus, and so that's why the protective layer. Also, you have sweaty hands, even if you didn't have sweaty hands, but the oils in your skin they have chemicals that can dissolve and pull the phosphorus off. So that's why you need that protective layer. With that layer there, you can seal, okay? You seal the phosphorus, and so you're not pulling them off. Eventually they do come off, but at least the protective layer can hold it for 5, 6, 7 years. All right, so leaving abrasions and strain from use. Screens will have scratches. When that happens, okay, when you have a scratch, say a nail just goes over the screen, you are removing the protective layer, and you're removing the phosphor layer. What will that happen to the image?
You also get that white.
Yeah,
Shows
you
an
will see it.
artifact.
So it's an area where you don't have phosphorus. And so that's an area where you're not gonna have nothing. That's gonna be an empty spot. There's gonna be a white line, okay, on that area, okay? So it's important not to have that. So white line artifact. This protective coat is approximately 10 to 20 micrometers, so also very, very thin. It's just, it's just a very thin layer. All right, so now let's talk about the phosphor layer. So I went the base, went reflective layer, I jumped the phosphor layer, went to the protective coat, and now I'm going back to the phosphor layer. This is the active layer. This is where the reaction, the physical chemical reaction will happen. Okay? All right, contains crystals that absorb X-rays and give off light. Okay. The thickness goes from about 150 to 300 micrometers, depending on the type of screens that you want to use. Just like films, I told you there were literally dozens of types of films. The same thing goes with the screens. The screens have different types, okay, many types. And when you combine all the different types of screens with all the different types of film you have, you end up with hundreds, literally hundreds of combinations you can make. Okay, and so that's in one of the items that make intensifying screens different. Okay, not only physically, but the type of reactions that will happen is the thickness. Okay, the first screens were made out of tungsten, calcium tungsten. Okay, and this is the type of screens that what's his name used? Edison used calcium tungsten. There was another type, barium, some other type. But calcium tungsten was one of the types they used, back in the 20s and 30s and 40s, yeah. And then later, okay, probably around the late 70s, 72, 73, is when rare earths really showed up. Okay, and this was a big revolution when it came to screens, because from that point on, even extremities were done with rare earth screens. The rare earths, if you look at the periodic table, you'll find them on the bottom. This is the bottom here. So some of the, not all elements can be used for intensifying screens. So some of the elements are used for screens. And there are some up here that also can be used, and they are all lumped together with the rare earths. And that's why they are called, collectively, they're called rare earths. And they work really well. All right, the phosphorus, when you look at the size of the phosphor, not the layer, but the phosphor itself, the actual grain, the actual phosphor, okay, is going to be between 5 and 15 micrometers. So very tiny, microscopically, okay, very small. Okay, their atomic number, it has to be, if you look at, they have high atomic numbers. Okay. For example, one of the common ones is gadolinium, and if you see gadolinium 64, pretty high. What's the other one? Yttrium. Yttrium all the way up here is 39. Europium is used at 63. So they're, lanthanum is also used. Yeah, use it high. Yeah,
High top
numbers.
numbers. Okay.
57. Yeah, so. Let me see what other ones use. Those are the common ones. Okay. And there is something called the conversion efficiency. Conversion efficiency refers to the ability, okay, of some elements to be able to transform a type of energy into another one. And that's what you have with these phosphors. They are able to absorb X-rays and turn it into visible light. Okay. Some of their conversion efficiencies changes. Some of them have very good conversion efficiency. Some of them they don't. It's never a 100% to 100% ratio. Okay. There is always some loss of energy. So, for example, if you have, I don't know, if the energy that is deposited into the phosphor is, I don't know, whatever number, say 100 ergs or whatever, what you get out is not going to be 100 ergs. You're going to get maybe 40, maybe 30. So, but the idea is that the conversion efficiency is the ability of some elements, okay, to absorb one type of energy and change it into another type of energy. All right? Yeah? Mm-hmm. Okay. Good. The spectral emission. The spectral emission is also it's a characteristic. It's a characteristic that the spectral emission is what it's saying is that each phosphor, each element has a very unique spectral emission. They will emit a very specific light, very specific color of light with different wavelengths. Okay, the one you saw, for example, was green, right? Bright green. But I told you that there are, you can have purple, yellow, light green, dark green, and that's because of the phosphor, the specific type of phosphor you're using. And the spectral emission is very important because you have to match, okay, that light wavelength. Your film has to be receptive, has to be specifically designed to absorb that wavelength. Are you with me?
Yeah.
Okay. If you come up, for example, if you just unknowingly you combine one screen with whatever film you found, it might not work. You might not have an image, or it might be a very faint image, or on the other hand, it can be a really dark image. You have to be able to combine it. Okay. You have to spectrally match the two, the screen and the film. And so the spectral emission is very important. You need to know, you need to be aware what type of, when I say wavelength, what am I referring to, guys?
Yeah, the line from one peak to another.
Okay. Yeah, but what, in your head, when I say wavelength, what are you thinking?
Picture of the wave.
Just
Yeah.
Yeah.
Okay. Good. I'm glad. Thank you for your honesty. And what the wavelength, thank you. What the wavelength is saying, where are we? What the wavelength is saying is it will give you a very specific color. Okay. All right. So when we go from the blues and the purples, they have a very low wavelength. As we move to the left, then the wavelength increases. Okay. And the frequency increases. I'm sorry. And now you're going into the reds. So by the time you get from the blues to the reds, what you have is the frequency of the wavelength has changed from very long to very short frequencies.
So red's really short.
Short.
That's
That
why
means
they
that it's
use-
more powerful.
That's why they use it in like dark rooms.
No.
Okay.
No, but the idea,
Okay.
keep that idea on the side of your head. We'll come back to that. But what
Nice long
I'm referring to is that the wavelength will change, okay, depending on the color that is emitted. Okay. Yes, Gary.
So red has, let's say, for example, has the longest wavelength.
Nope.
Is that
The opposite. Shortest. Highest the frequency. Shorter wavelength.
Or is it red?
Yeah. Yeah.
Sorry, what are the two, what have to match? The wavelength is color that's of the light being emitted by the screen and
The film has to be able to capture it.
the film has to be.
Yeah. So that's called spectral matching. Annie?
No, I understand.
Okay, good. All right.
Sorry, I keep
Yeah, what's up?
So short wavelength, but frequency is
When you, the
low?
shorter the wavelength, the higher the frequency.
Okay.
Write it down, I'll wait for you. And the opposite, right? Will be true. Got it? Good.
Okay.
So you're writing it.
I finished writing it.
All right. All right. Okay, good. Everybody finished writing, right? Monique, Rosina? No? Okay, good. Okay. Let's see, explain, direction, speed. Okay, here we go. Where's my pen? Luminance. All right, let's talk about luminance. Luminance refers, it is the ability of a material to emit light in response to excitation. Let me repeat that. It is the ability of some materials, it is the ability of some atoms, okay, to emit light in response to excitation. Okay, so all these phosphors, they have to illuminate. They have to be able to emit light in response to what?
X-ray.
X-rays, in response to the absorbance of X-rays. That's called luminance. All right, and I think it's coming up later, but I just tell you now because I might forget to tell you. When we talk about luminance, there's two types of luminance. You can have something called fluorescence. Okay, let me write this down. Fluorescence, okay, and fluorescence refers to instantaneous light emission. Okay, so it happens immediately, boom. Okay, that's called fluorescence. And then you also have, and they're both luminescence, right? So, put here, put small little dots here. Okay, so one of those is going to be fluorescence, immediate emission of light, and then you have phosphorescence. Phosphorescence is the emission of light, but it takes time. It's called afterglow. It's another name that is given, or screen lag. L-A-G, lag.
Screen.
Like when you have you're in a race and you're lagging behind because you're the slowest, right?
Slow glow.
All right, so slow glow. So what we want with screens, with radiographic screens, you want to be fluorescent. Phosphorescent is not good, but at least it's not good for screens. It might be good for other stuff that we'll study later. But next, but for now, is not good. So how do we determine if a screen or a phosphor is fluorescent or phosphorescent? Well, what they do, okay, what scientists have done, what physicists have done, is when you think of the atom, and this is the nucleus of the atom, and then you have electrons orbiting all around, right? And each electron has very specific orbits, right? So imagine that we stop time and we take a picture of this atom and we find this electron here, and this is the orbit of this atom. Comes here. So what they do is they measure how long it takes. Yeah, right. But they do. Yeah, it happens. Yeah, it can be measured. So you know, one orbit. If the electron is within one orbit around the nucleus, it's fluorescent. If it takes longer than one orbit around the nucleus, then it's phosphorescence.
Before it hits light?
Before immediate light.
So,
I'm sorry, can you repeat that last sentence? If it takes longer?
If it takes, imagine, all right, that we are able to take pictures of this electron moving through the atom, bunch of pictures, and then we see the orbit of this electron. If it emits light before or after reaching one orbit, still is called fluorescent.
Got it.
If it goes beyond that time, if it goes, okay, then it's phosphorescence. It's in Bouchon. Take a look at it. Read it. He does it in a couple paragraphs. Kind of hard to follow sometimes. I might have saved you what 10 minutes of reading. Nah, I'm kidding. It's a good one. Good. I heard some complaints. It's good. It's a good book. Just read it. The more you read it, it gets better. Yeah. Yeah. But that's why I gave you options, right? That's why I gave you Phosphor. That's what I gave you Carlton. So, but read both of them. But once you understand what Phosphor is saying or Carlton is saying, then go read Bouchon. Yeah. Yeah. All right. One more thing to explain here. What happens at the atomic level? Why are these phosphors emitting light? Okay. All right. Let me ask you this: are you exciting them with the X-rays, or are you ionizing them?
Exciting.
You're exciting them. And so, what happens at the atomic level? I think I hinted you at this before. What happens at the atomic level? What happens when an atom is emitting light?
The electrons are all moving closer to the nucleus.
No. Garrett?
They're just changing levels within their orbit.
Exactly. Good. That's exactly what happens. Within the orbit, they are not leaving the orbit. They're not going from K to L or from L to M. What they are doing is within the orbit, there are different levels, right? So within the K shell electron, within that shell, there is going to be different levels of energy. And that's what the electrons are doing. They're going boom. And then in the process of, not when they're going up, because when they're going up, they are absorbing energy, right? They need energy to move up to a little higher state. But then when they are coming back down is when they emit light. Okay? Follow me? So, if you have, this is the nucleus again. And if you have, this is one orbit, this is the second orbit. Within the orbit, you're going to have different tracks. Think of it as a different track. Okay? But they still belong to the same orbit, the same shell. And so what the electron will do when it absorbs energy, it will jump, say, from here, it will jump to here. And then in the process of coming back down, visible light is emitted.
Within the same shell.
Within the same shell. They are
Okay.
not changing shells, because if they were to change shells, that will be ionization.
Yeah.
They're not changing shells. Okay, they're just going to a different states. Okay? Where do they get that energy to go up? The X-ray. That's what the X-ray is providing them. That's what the X-ray is giving the atom. But it's not strong enough to get them out, to ionize them. In some cases it is, but that's not what we're studying here. What you're doing here is just exciting them, and then boom, they come back down and they emit light, visible light. Okay, are we okay? Okay, are we okay with afterglow, screen lag, phosphorescence, fluorescent, excitation? Okay, good. Luminescence? Okay. There is a little table in your textbook. Let me go back to the phosphor layer, just for a second here. Yeah, there is a little box in Bouchon. Look it up. I don't know what page, and if I knew, I wouldn't tell you. But look at the box. Go back and read that, when you're looking at the phosphor layer. And they talk about the properties of intensifying screens and high atomic numbers, for example. The conversion efficiency that I explained is the ability to turn one light into another. The spectral matching, the afterglow. And one thing that is important is humidity and heat should not have an effect on the screens. Okay, they should not. Okay, but sometimes it does, especially when you have low humidity.
Heat and humidity is more effective.
Humidity or heat should not.
Should not. All right. Well, you guys take a little break. You look a little tired. Take a little break.
Yeah.
Stretch.